Good afternoon, everybody. Welcome over to Room 5 for this afternoon session. My name is Chris, and I'm very excited to share with you this talk. It's like 10,000 streams when what you need is a queue. But firstly, big thanks to NDC. What a great conference. Hope you're all having a lovely day. And I know there's so many great talks that you could have attended in this time slot, so thanks for coming to mine. Who actually recognized the reference in the title of this talk, out of curiosity? Yeah, a few hands going up. Not everybody. I thought this was going to be something everyone would know, but maybe I'm showing my age, or maybe it's just my cultural bias. But I'm going to give you a QR code. This will take you to a YouTube video. You don't have to scan it, but if you want to, you can. And I'll give you a second. A couple of phones still up there. After the talk, you can rock out to some classic 90s tunes, particularly Alanis Morissette singing the absolute banger, Ironic. Does everyone remember the song now? Isn't it ironic? So if you remember the 90s, you might remember that there was some debate at the time as to how ironic actually some of the comments in this song were. I'm not going to get into that today. I used to be a skeptic, now I'm a believer. I think Alanis understands irony better than anybody. But yeah, today we're going to use this as a bit of a metaphor, but particularly the reference to the song. So give you an idea of some of the lyrics. It's black fly in your Chardonnay. It's a traffic jam when you're already late. And the iconic line, it's like 10,000 spoons when all you need is a knife, which is obviously the reference I'm riffing off, or as I like to say, it's like 10,000 streams when what you need is a queue. Isn't it ironic? So why are we talking about streams and queues? The reason is usually because we're interested in event-driven architecture. When we do event-driven architecture, we want to drive our architecture with this thing called an event, and so we need to understand what are the events in our system. I think one of the best ways to learn about the events in your system, to understand your business domain, is a practice called event storming, which starts with a huge pile of orange sticky notes, as I show on the screen there. And what we do is we write on these orange sticky notes what we call a domain event. Typically in English, we express it in the form noun-verb. So the thing that something has happened to, and then what happened to it, expressed in the past tense. And there's good reason for putting in the past tense, because events are supposed to represent things that have happened. They're facts about the past. So we might see something like order submitted or user registered. What we find when we get into this is that sometimes we need to represent things that are not facts about the past, but statements of intent about the future. So we also have commands. Now, events, they're obviously the headline act of event-driven architecture. Everyone talks about events, but commands are also very important if you're going to build a system based on messaging, which is what we're talking about here. So when you do event storming, it's a very interesting process. I do not have time today to explore it in detail, but you get a whole bunch of people together and you end up with something that looks a little bit like this, a collection of commands and events laid out in order of how they occur in your business. So here we've got a typical e-commerce domain, register user as a command, user registered. This pairing of what I want to have happen and then the fact that it did happen is quite common when you do event storming. We add items to carts, we submit our orders, and after we submit the order, the rest of it kind of happens automatically. So there's no more commands there, but the payment has to happen, then the order is considered to be accepted, shipped, and received. So this is a very massively simplified version of a kind of thing you might discover through an event storm. Once you've done the event storm, you can start to decompose it into what we call bounded contexts. This comes from the discipline of domain-driven design. Has anyone heard of a bounded context before? A few hands going up there. Yeah, it's a really interesting pattern. We'll be talking about it throughout this talk. This is, again, a simplified version, but you get the idea. Some of the process occurs in one bounded context, and another part of the process occurs in another bounded context. Now that we have our bounded context, we can consider what are the events being published to? Who's subscribing to the events? So we use this terminology. When we have an event, we have a publisher. The publisher advertises that this event has occurred, and we might have multiple subscribers. And this is cool because it means we can add more subscribers later to pick up off that same event and make other things happen without having to affect the publisher. So this changes the direction of coupling. It means that the publisher is not coupled to anything. The subscribers are, though, coupled to the publisher. So we haven't eliminated coupling. We've changed the direction of it. Because if you're using traditional sort of APIs or synchronous calls between your systems, then what you have is a sender sending a command to a handler. In this case, the handler is not coupled to the senders, but the senders are coupled to the handler. So directionality of coupling is affected there. But what we're here to talk about today is something a little bit more prosaic. We've got our order submitted event. Who just immediately defaults to thinking, oh, this is going to be a Kafka topic? Any hands going up? A couple? Yeah, Mr. Kafka down in the corner there. Who assumes it's going to be like a queue-based publish subscribe kind of system? Yeah, one, quasi, couple of hands going up. Excellent. And who thinks we're talking about event sourcing and event stores? A couple of hands going up. So a lot of people no hands going up at all. So maybe EDA is new to you, which is exciting. Hopefully this helps you get started in the right direction. I think in order to make a decision here, we need to turn to another sort of framing that I really like, which is called Philip Christian's 4+1 views. This allows us to consider our systems through 4 independent perspectives. We've got the process view, which is the runtime, deployable units. We've got the logical view, which is our bounded contexts and domain concepts. Development view, which is our source code packages, repositories, and the physical view, which is the infrastructure that it runs on. I do have some other talks more about this, which I recommend, but today we're going to focus on the logical view and the process view. And the reason being is that that orange sticky note belongs in the logical view. It's about the business domain. It's not saying anything about how it's going to get implemented, what it's going to look like at runtime. But on the process view, we have to make these decisions that we're talking about. So a streaming service like Kafka, queue-based publish, subscribe, or event stores. And if you're not sure what those things are, don't worry, that's what you're here to learn. So let's dig into it. We're going to explore first the difference between streaming, like Kafka topics, and queue-based pub sub, and we'll talk about event stores later, because they're a little bit different. So we're talking about, when I say queue-based pub sub, we're talking about tools like RabbitMQ, AWS SNS plus SQS together, Azure Service Bus, Google Pub Sub-ish. It's got some qualities of both sides. The most famous streaming solution is Kafka, obviously, but also AWS Kinesis, which is a wrapper around Kafka, and Azure has Azure Event Hubs. So all of the cloud providers have services that sort of fit one or the other of these two sort of messaging patterns. I'm going to start by looking at what do they actually have in common, because there are a few things that they do. First is that they're considered message brokers, which is just a generic term that means we store and facilitate distribution of messages. They typically organized around topics, which represent some kind of a thing that people can listen to, and typically there's some kind of message storage. They're not always separated, but the idea of a topic and the idea of storage are both part of both kind of brokers. We have producers and consumers. So something is pushing messages into the broker, consumers are pulling messages out of the broker. They consume those messages. Once again, we can think about this through the logical and process view, because in the logical view, we talk about sending commands and handling commands. We're talking about logical intent, or publishing events and subscribing to events. But when we're talking about the process view, we're talking about the data packets. We're talking about producing messages and consuming messages. So whenever I hear someone say producer and consumer, I know they're thinking about runtime concerns and the actual systems that are running in production. When I hear people talk about publishing and subscribing, I think they're talking more about business concepts and business domain ideas. So a bit of a hint there for you. They both have to worry about delivery guarantees. If you send 2 messages, how many do you receive? So you typically have at most once, where messages might get dropped, exactly once, where you hope that the messages are processed exactly once. There's a lot of subtlety to that. If anyone was in the talk earlier this morning about advanced pub sub patterns, there's some talk about the outbox, which is relevant for that. Or you can have at least once, where sometimes messages are duplicated. So in this case, message 1 is consumed twice. All brokers, streams and queues, both you need to consider these concerns and make decisions about them. But most of this talk is about what is different. So I've broken into 4 different areas: message distribution, scaling out, processing failure, and routing. So let's start looking at message distribution. What I mean by message distribution is who makes the decision whether a particular message should get handed to a consumer. And the biggest difference between the two, and if you're only familiar with one of them, it might be quite surprising to learn that the other operates in this way, is who keeps track of the state. So with queues, the broker itself keeps track of the state. It has a database or some other kind of storage, and it keeps track of which messages have been consumed already. Whereas with streams, it's up to the consumer to keep track of whether or not it has seen a particular message. And this affects everything else about how you work with these systems. The interaction as a result of this is you pushing to the queue or appending to the log. So with streams, the technical term for them is actually a distributed log. So you're either pushing a message into the queue or appending to the log. But when you're consuming on the right side, with queues, we say pop off the queue. That's a stateless operation. I don't need any information. I just ask, what is the next message? But with a log, I have to say, I would like to read the next message after offset X. That X, that number representing the offset, that's what I mean by the state. So the consumer has to keep track of that state and request the next message after that state. So let's look at an animation of what this looks like. So we've got messages flowing in to both the queue and the distributed log. 2 messages, and then we have the queue popping off, they get message 1. We have the distributed log saying read from offset 0, it gets back message 1, and it updates its offset state to say message 1. And so then we have a third message pushed in. B says pop off the queue, D says read from offset 1, and it gets back message 2. Pop off the queue, gets the third message, read from offset 2. So you can do the same kind of thing with both of them. You can have 3 messages pushed in, 3 messages consumed, but the way they did it was very different. Now, if you know something about Kafka, you'll know there that the distributed log still has all of the data. It's not tracking the read state. It's just keeping all the messages so that anything else can come along and say, I would like a message from a given offset. But the queue is now empty, and that's what I mean by the state. It's now empty, so it's not got any more messages to give. If anybody else says, give me the next message, there's nothing left to provide. Technically speaking, the thing that makes the log consumer a stateful consumer and the queue a stateless consumer, but talking about the stream consumer as stateful, that state often is stored back into Kafka, which confuses people because they think, oh, the state is in Kafka, so Kafka's managing it, but it's actually not. It's stored in Kafka, but it's managed by the consumer, and usually your client libraries take care of it for you. But it doesn't have to be in Kafka. Technically, you could store it anywhere, and the actual Kafka mechanism of storing the data and producing it and allowing it to be consumed would operate no differently. So this leads me to my first irony, because if we look at this thing, we can see that with queues, data is flowing into the queue and then out of the queue and getting deleted. Whereas with the log, the data is going into the queue and staying there and not moving, and it's up to everybody else to come and get it. And yet I find it ironic that Confluent advertises Kafka as data in motion, because I think that data in motion applies much more accurately to queues than it does to streams. So Alanis can help us out. It's like your data is staying still when you thought it was in flight. It's an it ironic. So just one of the first sort of ironies I find in this space, because as you'll start to see, a theme through this is not necessarily that Kafka's bad, it's just that a lot of people who have adopted it have started using it for everything, and because of some of the advertising that's been out there about it. So hopefully this will disambiguate those cases. The next difference, consumer scale out. So because queue consumers are stateless and stream consumers are stateful, we need to manage scale out differently. When we think about scaling out a cluster, if you've ever worked in the web tier, and especially if you've been around for a while, you might remember content-based routing, so session ID cookies and sticky sessions in load balancers. Anyone with grey hair remember having a sticky session load balancer? Thankfully, we don't tend to do that anymore, right? Because we realize that stateful nodes in a cluster is a bad idea. It's very hard to scale in and out. So most of the time, we have stateless web tiers. The state still has to go somewhere, usually in a centralized database, but we can scale out the web tier and route requests to any node. But with stateful clusters, individual nodes have to process specific requests because that's where the state is. So stateless in a web tier is like a queue. Stateful in a web tier with sticky sessions is like a stream. We also have other scaling patterns for stateful clusters. So if you look at other stateful systems like databases, the way that they get scaled out is typically sharding, where you have part of your database split up. So some records are in one database instance, others are in another. Or you have traffic type splitting between read and write nodes in a database cluster. Or you have some kind of worker allocation with quorum election and all this kind of stuff across some distributed databases. And when we talk about streams like Kafka, it uses those two patterns, sharding and workload allocation. So let's look at how it does that. If we scale out our consumers, so now we have 2 nodes of consumer B and 2 nodes of consumer D, and we have a message in the queue and a message in the stream, when we pop it off the queue, you'll see that B1 gets the message and B2 does not, because the queue is keeping track of it and saying, I've already given that message to someone, I'm not going to give it to anybody else, which is kind of what you'd want. With a distributed log, if you use what's called a low-level consumer, and they are both allocated to this same distributed log partition, you're actually going to get that message read twice. So this is typically not what we want. If they are both instances of the same service, you typically only want the message processed once. But because they're sharing state, they are going to process that message twice. Now, this doesn't typically happen when you use Kafka because there's some smarts in the client library to manage it for you. But this is what happens if you engage directly with Kafka and bypass that client library. So the solution, though, to avoid the message being processed twice is you do that sharding operation, or what they call in Kafka partitioning. So let's imagine we have 2 partitions. Our producer needs to have an algorithm to allocate messages to one or the other partition. And so in this case, we're just going to go back and forth. So message 1 is in partition 1 and message 2 is in partition 2. Message 3 goes back to partition 1. Now, because D1 has an offset record and D2 has an independent offset state, they're not going to duplicate the messages. D2 is only going to read from partition 2, D1 is only going to read from partition 1, and so now each message is only going to get processed once, which is what you want. And this is typically what you see in Kafka installations with that high-level consumer. If we have another message that comes in and then another, what happens if D2 fails? Oh, apologies, there's a typo there. The top one should be D1. If one of them fails, then the messages from partition 1 are going to keep getting read, but the messages from partition 2 are not going to get read. So we're going to have messages that get skipped and missed. Whereas with the queuing system, it's just going to pop off the next message in the queue. So all of the messages get processed without any regard, whereas with the distributed log, message 4 is never processed. Unless you introduce this high-level consumer concept, which is part of the client library, that uses sort of a leader election process, and after a few seconds, it detects that one of the nodes is no longer online, reallocates that partition to D1, and now D1 is actually monitoring both partitions. So there is a way to resolve that using that sort of high-level consumer repartitioning algorithm. But one thing you can't solve is that if you add a third node to the cluster, with the queue, it immediately adds to the processing capacity. But with the distributed log, it's idle until you reallocate your partitions. And this is the reason that in a lot of Kafka installations, people pre-allocate way more partitions than they currently need because they want to allow themselves the opportunity to scale out their consumers further down the road. And I think that's a bit of a guessing game, and of course, at some point you may still exceed that partition count and have to reallocate and redistribute data across your partitions, which is a bit frustrating. So, turning back to Alanis, it's when you need to scale up, but your partition count's too low, isn't it ironic? What's different with message processing failure? So we talked before about node processing failure, but when we talk about specific messages, if we have a message coming into the queue and the log, building up a little bit, and then we pop off the queue and read from offset 0, I kind of skipped over a step before. What actually happens is, while you're processing that message, there's this idea of an intermediate state. With the queuing system, it's sometimes called message visibility, and what will happen is, while it's processing, the queue actually holds onto the message, but it won't release it. It considers that message to be invisible. And so it won't share it with any other processes while it's being processed by B. With the log, the way it works is just that the offset is not yet committed. So you're basically saying, I'm still processing message 1 and I haven't yet updated my offset. So if anything goes wrong, I should be able to go back to message 1. If it's all successful, then there's actually an explicit acknowledgement with the queuing system where it goes back and says, actually, you can delete message 1 now. Sometimes called an ACK. There's various words for it depending on the system. But either way, it's an explicit confirmation that it's been successfully processed. And with the distributed log, the way we keep track of the fact that it's been processed is that we commit that offset update, which is often done asynchronously, which can have other challenges as well. If we process message 2, and it turns out that there's a failure while we're trying to process message 2, maybe we have a temporary connection issue with our database or a downstream API, or maybe actually there's something faulty with the message, we can't deserialize it, then what's going to happen is that with the queuing system, message 2 will eventually get made visible again. So there's usually a sort of a timeout or some sort of a condition that allows that message to be resurfaced to other consumers. With the distributed log, it's a bit different. The default is actually to skip the message. So the offset gets updated whether or not it was successfully processed, and as long as you don't allow your process to fail completely, and you can go around your read loop, you'll actually just get the next message. So you'll skip the faulty message. The offset of the failed message is actually kept in memory, and eventually, once you do successfully process a message, that'll get committed. And so unless you do something special, you're actually just going to skip over that faulty message. If you want to retry the message, then you have to explicitly seek back to the message and say, no, I want to stay at offset 2 because I haven't finished dealing with offset 2 yet. So that's called a seek operation. And then eventually, if it is successful, then you commit the offset and you're allowed to move forward. But if it keeps failing over and over again, well, with the queue, we have a special capability, which is that the queue will keep track of how many times it's been attempted to be processed. So if a given message is attempted to be processed, say with RabbitMQ, it's 20 times, if you configure it, it'll forward that message to a dead letter queue. And then you can have something else keeping track of that queue, raising an alarm, allowing manual processing, and reintroducing the message back into the queue to make sure it does eventually get processed. But with the distributed log, if you have decided that messages are important, so you're going to keep reseeking back to message 2 until it gets processed, and it never actually successfully processes, then you have to explicitly and manually deal with it. You have to set up a dead letter queue, you have to keep track of how many times you've retried it. You can't store it back against the message because these messages are immutable in the distributed log. So you need some other kind of state storage to keep track of how many times you've processed the message and eventually forward it to a dead letter queue. So there's quite a lot of work you have to do if each message is important to you and you don't want to let it slip away. If you do this and you don't handle it properly, then you can get what's called head-of-line blocking, which is where a faulty message can hold up all the messages coming after it, and the consumer is sort of stuck there trying to process over and over again without sort of knowing what to do. And this hits a lot of teams when they first get started with this and haven't really considered carefully how to handle these failure scenarios. So another lyric of irony, a new dev team adopted EDA, got head-of-line blocking on their very first day, which is impressive actually to have enough volume to get that on the first day. So maybe we should give them some credit. Let's look at message routing now. So this is an interesting thing. This is actually where the concept of events and a command starts to come into play. The topologies are actually quite different between these systems. So with the queuing, I've just been showing the queue so far, but there is also a thing called a topic. In RabbitMQ, it's called an exchange. In Amazon SNS, it's called a topic. And what happens is when you publish that message to the topic and you have subscribed the queue to the topic, it gets forwarded across. With the streams, it's basically one and the same thing. When you add it to the topic, you're appending to the log, you're just doing one operation. There's no separation between the two. But with queues, there's actually just two separate ideas, the topic or the exchange and the queue. After that, once it's in the queue, once in the topic, everything happens as we've discussed. If you do want to have multiple subscribers, so in this case now we're not talking about 2 instances of B, but we're actually talking about 2 separate services, so B and E, or in the streaming world, D and F. Well, with DNF, they have independent offset management, so they are keeping track of it separately. With the queuing world, you actually have 2 separate queues. We often call them the input queues. So what we do is we map the topics to the events and the queues to the consumers, and each consumer gets its own queue. So we sometimes call those logical subscribers. If you're thinking in the streaming world, though, they're often called consumer groups, because when we talk about Kafka, each node is a consumer, so a collection of them is a consumer group. In the queuing world, we tend to think of the consumer as more of a logical collection of nodes. So don't get caught up on the different semantics there between the single and the plural. But if we publish to a topic, then what actually happens is 2 copies of the get message get copied out there. So one copy goes into B queue, one copy goes into the E queue. Whereas with the streams, there's just one instance of the message sitting there in that database. And so with 2 copies of the message versus 1. That allows B to pop off its queue and process that message, and E to pop off its queue and process that message. Whereas with D and F, they're both reading from their offsets, they're keeping track of the offsets independently, so they both read message 1. So remember before I said it's a problem when you have the same message processed twice? In this case, it's not, because D and F are different services. They should be doing different things with the message, and actually you do want it to be processed twice so that the 2 different things happen. And this is actually one of the hallmarks of event-driven architecture, is you have multiple subscribers doing different things when a given event occurs. So you might remember this from earlier, where we have our publisher publishing our event. But what about that command? Remember I said commands are quite important? Well, with the queuing system, it's pretty straightforward. You just skip the topic. If you're sending a command, you're sending it directly to the service that you know can handle that command. So you just put it straight onto the queue that belongs to that service. And that way, E doesn't even get that command, which is what you want, because that's the logical intention, is that you have this fan-in, multiple senders sending the commands to one handler. With streams, it's a little bit trickier. Because there's just got this one concept of a topic, you have commands going into a topic. And then there's not really a native way of making explicit or clear that this should be treated as a command and only ever handled by one consumer. So you need to be careful with the access control lists or maybe some kind of convention that allows you to make sure that you can trust that those messages in that particular topic, which are actually commands, are only going to get processed by the one thing. Whereas when we go back to events, we have the fan out through queues and streams. So one more bit of irony, I think. they call them sending commands through a topic and called them command events. Now this is a reference to some documentation from Confluent where they actually called messages on such a topic a command event because they were so used to calling messages on topics events, and they weren't disambiguating between that logical intention and the messages in the process view. And I think the whole notion of a command event is just like, WTF, guys, seriously. A command and event are completely different things. We should treat them seriously and disambiguate them in that way. So let's summarize those differences between the broker types. Message read status tracking, with queues, it's done by the broker. With streams, it's done by the consumer. Poison message handling, automatically handled for you by the broker. With consumers, you need to write some code to do it. You need to make some decisions about how you're going to process those poison messages. Are you just going to skip them, or are you going to manually forward them to some sort of dead letter queue? Can you auto-scale your consumer clusters? With queues, absolutely, very easily. With streams, I'm going to say no because you can't automatically or dynamically scale beyond the partition limit. Technically, within the partition limit, you can do a degree of automated scaling. Can you automatically recover from consumer process failure? With queues, yes. With streams, yes, because the client libraries do the heavy lifting. But again, there's some delays there for the leader to detect and reallocate partitions. Do they have support for the semantic concept of commands versus events? With queues and topics, yes. With streams, no. What about storage of historical messages? I haven't discussed this explicitly, but you've sort of seen there that with Kafka and streams, the broker stores those messages for you. And this is obviously one of the things that's very appealing to teams, the idea that the whole history of our event log is kept there, and we can always spin up another service in the future and replay messages since the start of time so that it can do what it needs to do. But you need to be careful if that's actually what you want to have happen, as we'll see in a moment. And that relates to, can new consumers access historical messages? So with a queuing system, if you do need that, you need to take care of that manually. And it's quite common to have like a separate dedicated auditing queue where once messages are handled correctly, successfully, a copy gets put onto the audit queue so you can store it and index it somewhere so you've got an audit trail of successfully handled messages. So different ways of dealing with the same kind of things. But now let's look at that third thing that I talked about at the start, event stores. So now we're starting to talk about a thing called event sourcing. If we think about queues and streams being about inter-process communication, passing data from producers to consumers, event stores are totally different. And this is something that a lot of teams get caught up on. Event stores are actually about storing your system state as a history of events. So remember we said we've got like a command like submit order and an event like order submitted. Well, in order to handle that command, we actually have a thing in the middle, which in DDD terms is called an aggregate. And the aggregate is the collection of state that allows us to decide what to do when this order is submitted. Is the order in a valid state to allow it to be submitted? Has it already been cancelled? Maybe there's some rules. You can't submit an order that doesn't yet have any items in it. All those business rules are encapsulated in the aggregate, along with the data about the current information of the order, or the shopping cart, or whatever you might be calling it. So there's different ways of storing that state. The traditional way is to use a relational database, and each record represents one aggregate, an instance of an aggregate. So you get an ID and a bunch of data. For a long time now, NoSQL has been quite popular, and so each instant is a key, and then you have the data stored in some sort of JSON serialization in the blob store. Event sourcing is the other way around. We don't store the state, we store the history of the events that have occurred to that entity. So it might be order shipped or payment successful in a record, but it actually looks a lot like a relational table because it kind of is. It's indexed by the ID of the aggregate or the entity, and it's got data associated with the type of the event. So when we say state and events, if we are storing data in relational tables, we can still have events, but those events are typically produced as a side effect of updating the state. We update the database record, and then we publish an event to say, hey, I just updated the database record. I've flipped a bit from not submitted to submitted, and I'm going to publish an event out to the world now saying this order has been submitted. But with event sourcing, we do it the other way around. When we decide that the order should be submitted, we actually add an event record, order submitted. If we now get another submit order command and we want to know that we shouldn't allow it to be processed because it's already been submitted, what we do is we load the history of those events, we recompute this current state on the fly, and so we treat the state as a side effect of having persisted the event. So we've got these different mirror images of each other. With state persistent, the events are a side effect of the state being updated, and with event sourcing, the state is a side effect of the events being persisted. Now, one of the reasons you can see why this is quite confusing for people is when you start talking about keeping a log of the events that occurred to an entity, you might look at Kafka and say, that's about storing a log of events. That looks like it might be a good solution. But you have to be really careful here. Distributed logs are optimized for querying by topic and offset. That's what they're all about. They're all about, give me the last message on this topic. Event stores, dedicated event stores, are optimized around, give me all of the events that have occurred to this particular instance of an entity. You cannot get that out of Kafka. You can't index it by entity ID or aggregate ID or key or whatever we want to call it. You can't say, just give me the subset of messages that relate to order 1, 2, 3. But with event stores, you can, and that's what they're optimized for. So they look kind of similar at a distance, but when you get close to them, they are fundamentally very different. And another irony, unfortunately, in 2017, Confluent advertised messaging as the single source of truth and talked about Kafka being a great solution for event sourcing. When you look at exactly, what they did there, it's a shame. But once again, we have another irony. It's an event streaming log when your state's out of date. They had some more documentation about event sourcing later, which got a little bit more nuanced, and they actually sort of acknowledged that not all of the events in your event sourcing storage need to go public via something like Kafka, and they introduced this concept of domain events versus integration events. But as we'll see in a moment, I think this is a bit of a mistake. Even this terminology is leading people down the wrong path. But thankfully, they did walk back that 2017 article because a lot of teams were trying to do event sourcing using Kafka and having a lot of problems. But let's go back and now look at what about this event storm, this series of events going from left to right that represents our business domain, can help us make some good decisions about what kind of technology to use. Well, you might recall that we're going to divide it up into these bounded contexts. So we've got a shopping cart, payments, and shipping. If I shift the edges a little bit, then we can start to see that some of these events actually need to flow from one bounded context to another, because the order submitted event needs to get handled by payments in order to start processing payment. And when the payment has been processed successfully and the order is accepted, then we need to have that handled by shipping so that it can actually initiate the shipping process. So we can start to see there's two very distinct types of events in the business domain. Before we even start to talk about the technology, we've got private domain events and public domain events. And this is why I don't like the term integration event, because integration event has you thinking about integrating systems and talking about the technology layer. And we need to start thinking about the business domain, thinking about the kinds of events that we discover when we have these collaborative sessions with our business stakeholders and learning about what matters to them. So we've got private domain events and public domain events. And now we can start to think about what are the different technologies that are well suited to these different types of events. Let's look at private domain events first. Typically, you'll have lots of data on a private domain event because it is the state record, particularly if you're doing event sourcing. So if you want to use those events as the source of truth or the historical record of the bounded context, you want to use an event store. That's it. No ambiguity. If that's your purpose, is to use those events as the source of truth, it's an event store. But you don't have to do that. You can still use relational databases. They're totally fine. They still work really well. If you want to use that event to trigger the next step in a workflow, and by a workflow here, I mean like an internal workflow, so we're talking about business process choreography, every event is critical, right? Imagine if an order payment required event was dropped or an order submitted event was dropped. That would be a big problem. So as you've seen from the failure modes that we saw before, a message-based, queuing-based pub subsystem is oriented around this kind of situation where each message is critical. You've got your dead letter queue, you've got the ability to scale out without dropping messages, you've got all sorts of capabilities built into the broker that are oriented around making sure that every message gets processed successfully eventually, which is great. But sometimes that's not what we're doing. Just to be clear about that, if you are using queuing-based pub sub to orchestrate a business process, but it's all part of the same bounded context, then what you end up with is two runtime nodes that are part of the same bounded context, and that's totally okay. If you're looking at your runtime processing nodes and you're not sure which bounded context they belong to, that's a real problem. I think you need to get onto that and start thinking about the fact that a collection of runtime systems belong to a single bounded context. That means they're all processing everything that's within that boundary. They all have access to the same domain models and usually the same data storage. So in this case, the producer and consumer belong to the same bounded context. But there's another kind of thing that we often see our businesses asking for. And it's some things like, stream analytics, Internet of Things, click streams, anomaly detection, moving average windows, threshold crossing, some kind of statistical aggregation. In this case, the individual events are less important than the stream itself. How is the data changing over time? We don't mind if we drop an event. What we're looking for is the efficient computation aggregating over a series of events for the whole business. And that's what stream systems are designed for. So Kafka is actually really good for that. And there's other solutions like Kafka Connect and Flink and KSQLDB that can sit on top of a Kafka stream and give you exactly the kind of outcomes that you want when what you're focused on is this kind of stream analytics, but not business process workflow orchestration. And once again, though, in this case, if it's a private operation of the bounded context, it's totally fine for both of those, producer and consumer, to belong to the same bounded context. So let's think about public events. This is just a heuristic, but as a rule of thumb, I strongly recommend that your public events are very lightweight and don't carry all that data with them. The more data on a public event, the more risk that any changes to the schema of that data are going to affect all of the downstream consumers. Everyone thinks, oh, we're doing EDA now, we're loosely coupled, isn't that great? But actually, the coupling is still there, as I showed before, it's just in a different direction. So if you want to start versioning your events and changing the schemas of those events or introducing new events, all of your subscribers need to update themselves to handle that new version. So one way to minimize the risk of that is to put the minimal amount of data that you possibly can into what's often called like a lightweight notification event, which matches very well with the needs of this kind of public event that's flowing between your bounded contexts. So if we're talking about using events to allow subscribing bounded context to react and execute the next steps in a business workflow, like we saw, flowing from shopping cart to payments to shipping, well, every event is critical, so what do you think I'm going to recommend here? Queuing-based pub subsystems, once again, because that's what they're all about. And in this case, though, the producer and the consumer are typically different bounded contexts, and that becomes a public information exchange. So this is something that I think is really important and not enough teams are doing. Even when you're using a queuing system, some of those queues and topics might be considered private to a bounded context, and some of those queues and topics might be considered public to the bounded context. And you really need to find a way, whether it's through naming conventions or maybe only publishing those private events into async API specifications as ways of making sure that other subscribers don't inadvertently subscribe to your private events. Because with your private events, you're probably going to assume that you can change them at will because you're the only consumer. Your team is the only consumer. But once you start publishing them publicly, it's really important to make sure that you know that they should be treated like a contract and they're going to a different bounded context. There's another kind of scenario, though, with public events where we do want to put a little bit of data on it. And I typically try and avoid this if possible, but sometimes it's not possible. And I actually say here with a question mark next to the domain event, because you might have an event like customer address updated. Customer address updated is not an event that anyone in your business domain cares about typically. So some kind of just record updated, what we call CRUD events, create, read, update, deleted. Those are things that your business stakeholders shouldn't be concerned with. If you notice, all of the other events that I've had here in commands, they didn't use verbs like updated and deleted. They used verbs from the business domain: registered, submitted, accepted, payment successful. Those are terms that mean something in that business domain. But sometimes you find yourself with an event that is literally just, this data was updated and I'm not going to tell you anything else about it. Sometimes this comes out of like a change data capture situation off a legacy database. And so you have these large complex data structures with commensurate risk of changes affecting the subscribers. Sometimes this is known as event carried state transfer, where the point of the event is actually to ship a whole bunch of data from one service to another. And because of the design of your system, typically a legacy system that was designed without much modeling around what should and shouldn't be public and private between bounded context, if it had any consideration of bounded context at all, but you end up with something like this. So a stream or a distributed log can actually be a very effective solution for this, because the individual events typically don't matter. Later events supersede them. The whole data set is on the event. So you're not really too concerned about stale data. You actually want fresh data. You just want the most recent record. So you might be publishing from like a customer bounded context and having an address updated and using something like Kafka Connect to materialize that data into what you might call a forward cache that's available to the downstream service. And this can be quite effective because it can reduce the amount of requests that otherwise the shipping service would be having to make API calls back to the customer service all the time to get that address. By using a solution like this, you can materialize that data in a way that's available to the shipping service, and you might see this referred to as a forward cache. I would recommend you try and avoid this if you can get away with it, but sometimes you find yourself without any alternative. So let's summarize those heuristics that we went through. If we're talking about state management, we should be only talking about private events, and we should use an event store, and we shouldn't have anything or any concern around being public. If we're talking about business process workflow orchestration, whether we're talking about processes that are internal to a bounded context or processes that flow across bounded context, we should be talking about queue-based pub/sub, because that technology is oriented around every message mattering and each message needing to get processed eventually. If we're talking about streaming analytics, we're talking about distributed logs. That's actually what it's for. So use it for what it's for, because in those situations, typically skipping a message is actually a good thing to do. And some of the other overheads that you deal with partition management and so on, they're kind of worth those overheads to get the benefits of maybe it's the throughput or the kind of freshness of processing of the real-time analytics that you want out of that process. And finally, if we're talking about some sort of forward caching, then yes, a distributed log can help you there. But again, you need to be careful about treating that as a public operation. Those events are a contract. They need to be versioned and managed like so. So, going back to the original lyrics of this song, I do hope that this talk becomes the good advice, or doesn't become the good advice that you just didn't take. I do have a GitHub repo that has examples in C# of all of the scenarios that we talked about. It's got generic broker interface and implementations for a few different patterns, and you can see how each of those brokers handle things like message failure and scale out to the partition level or beyond the partition level. So check that out if that's of interest to you. Some of this actually comes from a training course that I offer called Imagine the Future and Build for the Now. The full agenda over 2 days includes a lot of discussion about domain-driven design in the logical view, but also a lot of talk about inter-process communication, which is what this talk draws from, as well as the developer view and how to orientate your developers so that they can make sense of what's public and private, what belongs to which domain or subdomain, and which belongs to which runtime process. So I'm going to run this in October through DDD Academy, but if you're interested, please reach out. We can do private sessions as well. And that's it and all. Thank you so much for your time and attention. Please do connect. This will take you to my website. The social media handles are all there. I love talking about this stuff. If you've had any experiences in production with these things and you'd like to share them or tell me that you think I'm wrong, that's welcome too. And I'll be hanging around for the next day as well, and would just love to have a chat in the hallway anytime. So thank you very much. Enjoy the rest of your day.